So we left off last time, it's been a little while, but we left off last time talking about transformers. And I wanted to bring this example in. I think this is a good example for lots of different reasons, but to show you that transformers exist for other things just besides stepping down voltage or stepping up voltage or something like that. We certainly use it a lot for that. But you can find transformers in lots and lots of places. An induction furnace is actually a good example of a transformer. It's a little bit hard to find the secondary and the core. But that's a good example. This one with a movable core, I'm kind of a mechanical person, so I like things moving. So an example here is that we have the primary coil, so this would be the primary, and I have a couple of secondary coils. This might be S1, and we could say that this is S2. And you could imagine that when the core is pulled more to this direction, so the core is sitting down here, the coupling is stronger between these two coils, right? Okay, which would give you a negative value on voltage, depending on how we take negative and positive, but we might get a value here. So if this is A, we could say that this is A. So I would have some negative output. And then if I move the core, so I shove the core the other way, so now the core is sticking out over here, I would have more coupling between those two, which would give me some value here. If I say that this is B, I could say that this was the B value. And the nice thing about this is it is linear, okay? And oftentimes we'll call this an LVDT, stands for linear variable differential transformer, okay? You can imagine if you're trying to find the position of something, this could be very valuable. You attach the core to it, so maybe you have a milling machine or something, and you want to know exactly where something is. The table you attach to this core, and as it moves, it's pulling that core in and out of the transformer, and it gives you a nice linear relationship. A lot of relationships are not that linear. I mean, a spring is linear over short ranges. If we start to look at long ranges, it's probably not going to act very linear. However, this is a very linear relationship. This is absolutely linear and kind of nice. So I wanted to point that out. Having cores move is not uncommon. Those of you that have ever maybe done some welding and you've adjusted the amperage on a stick welder, when you've turned the knob, oftentimes you may have adjusted the position of the core. The knob goes in and changes the core to adjust the coupling between the primary and the secondary. So having a movable core is kind of interesting. So I don't want to go through this problem and analyze it too much. I don't know that we're at that point yet, but I just wanted to show you that we use this for a lot of different phenomena. This could be used to keep track of the position of something, an LVDT. Those of you that go into instrumentation may see that again. Questions with that? So useful things. So this is going to be probably more of mechanical. Let's figure out what to do with the dots. We spent quite a bit of time last time talking about the dots, and I didn't put the dots on this LVDT because I was just trying to think of it conceptually. But we want to take it to the next step eventually and look at something very specifically. We talked last time about how we could physically, if we were to do an autopsy, so to speak, on a transformer, take it apart and assign the dots. We talked about how in lab this week we'll be doing experiments that will show us experimentally where to put the dots so we don't have to take the transformer apart, because that'd make it kind of an expensive lab, although I guess you'd get your lab fee out of it. But what we want to do is, having put the dots in position, whether we've done this by experimentation or by taking it apart and looking at it, what do those dots mean, and how do we use those dots? And our convention is this. And again, I'll be posting this after class. If you don't want to write all this down, it'll be posted in PDF form. But it says, when the reference direction for a current enters the dotted terminal of a coil, the reference polarity of the voltage that it induces in the other coil is positive at its dot. So if the current in the secondary enters the dot, it's going to induce voltage in the primary that is positive at that dot. Okay? And of course, vice versa. I didn't want to have to copy the whole thing down the other way, so I just said vice versa. Questions with that? Now, our other conventions are still in place. I mean, we're going to use mesh analysis on most of these problems. We're probably going to take gains as negative. Those conventions that we've been using for weeks and months are still in place. We've just added this one. Any questions with that? Well, let's see if we can put this in play in terms of an example. So I've got an example here. I've got the mutual inductance in phasor form. Nothing really new except for this piece here. Remember that the mutual term M is equal to the coefficient of coupling K times the square root of L1 times L2. If you're trying to have an efficient transformer, you want your coefficient of coupling as high as possible. And then what we do here, so we could say that we then have J omega M. You take that M value and you multiply it by J omega. Just like you would say J omega L, we're going to have J omega M. So that's where that came from. Whatever the omega was, whatever the M value was, we multiplied those together and we got J1 ohm. Okay. So I've got this little circuit here. I've got a primary and I've got a secondary, and I'd like to find the voltage V0 on the secondary side. Okay. And what I do with these is I do them just like we would have really at the end of last term, right? I mean, I don't know, it would have been a very nice question, but this would have been, except for the mutual part, this would have been a fair question on the final from last term, right? So let's go through this one. I've got an assumed current I1. I'll start through here. I'm going to go ahead and take drops. What do we usually say? We say drops are positive? Yes?
Are these, between the two dots, are those inductors across from each other?
Well, this is an inductor. And that's an inductor. Because they have self-inductance and they have mutual inductance. Okay, so I'm going to take drops as positive. I'm going to be real clear about that. And I'm going to go ahead and let me look at loop 1. So if I start there, I have a gain of 10 at 0. So I'll say that's minus 10 at 0. Okay. So that's a gain. That gets me to this point. And then what's going to happen? I'm going to have a drop. So I'll say positive 1 times I1. And then I'll have another drop because of this self-inductance here. So positive J1 times I1. And oftentimes I'll just combine those as 1 plus J1 times I1. But since this is our first problem, we'll do it a little more piecemeal. And if we didn't have to worry about the mutual portion, this would be done, wouldn't it? That would get us back to this point, and we'd be done, wouldn't we? We'd set that equal to 0, say that's what Kirchhoff wanted us to do. So these are all the self terms. And like I said, that would be a fair problem on the first exam. Maybe even a fair problem for last term's final. But now I need to add the mutual term. So I know that I have this current I2 that is going into this thing. That current I2 is entering the non-dotted terminal, right? So which terminal is going to be positive over here? Yeah, if it enters the non-dotted, then the non-dotted becomes positive. If it entered the dotted terminal, the dotted would become positive. So by this I2 entering here, this becomes positive. And as we came around here, so we're going to have this term, we're going to have this J omega 1. So I'm going to have J omega M, which is J1. That's J1 times I2. And if we went around, it was positive here, so it had to be negative there, didn't it? So was it a gain or a drop? As I move around this thing clockwise, it becomes a gain, doesn't it? So how do I treat gains? Yeah, negative.
That's part of the same. So is it negative when it's going into the J2 ohm inductor? Is that entering negative by observation that the other is positive?
Well, it enters the terminal that does not have the dot. Okay. So now I come over here and I say the terminal that does not have the dot has to become positive. Okay. Yeah. Because what do we say on the this thing? When the reference direction for a current enters the dotted terminal of the coil, the reference polarity of the voltage that it induces in the other coil is positive at the dot. So we could also say, I mean, the vice versa. I'm going to say if it enters the non-dotted terminal, it would induce voltage that's positive at the non-dotted terminal of the other one, right? Okay? So I come up with something like that. Questions with that? Yes?
You say just in general, the voltage is positive at the point at which it enters.
Well, because this current here, I2, enters the non-dotted terminal, the voltage would be positive at the non-dotted terminal. So, I mean, I guess you could say that it's positive at the terminal that it enters. But you're still going to have to use the dots to figure it out. Okay, so let's try loop number 2. So loop number 2, maybe I'll start up here and get some momentum. I've got 2 ohms and another 2 ohms. Why don't I just call that 4 times I2. Everyone's good with that? 2 plus 2 is 4. Then we've got this one, plus J2 times I2. J2 times I2. So I've got the resistance, I've got the self-inductance, and I would get back to this starting point. I'd be done if it weren't for this piece over here. So now I have to do the mutual term, and this I1, it does what? It enters the dot, doesn't it? So what's that going to make over here? It's going to make that positive. So we would go from, as we went around here, we went from negative to positive. What's that? Yeah, so we said drops are positive, gains are negative. So we have a negative J1 times I1, and that's equal to 0. So we have all of these self terms, and we have this as the mutual term, and we have this as the mutual term. And you have to use not only the convention that we just talked about with the dots, but you still have to go back and carefully use this. You'll notice I wrote that out for the first time in a long time, right? You have to carefully use that. Nothing new here. This is old, old, old. But you still have to use it. Yes?
So, you let's go over the, so it's going in the dot on the left side.
Okay, so we're working on, you're talking about this loop equation number 2? Okay, so I did all of the self terms. That was this 2 and that 2, so I just combined them into 4, and then I did this one. Okay, and then the mutual term's the sticky one. So this I1, it's coming around and it's going into the dot, isn't it? So if it's entering the dot, it's going to induce voltage that is positive at this dot. Therefore, it would be negative there.
So is that the vice versa term or the first one?
It is, yeah. No, the first one, the first one I'm using the vice versa. The second one I get to actually use it's entering the dot. So I just get read it verbatim. Okay. Now, we're still not home yet because I've got this voltage here that's being induced. And as I go around this in the clockwise fashion, I'm going from negative to positive, which gets me a gain. And I treat gains how? Gains are negative. Okay. Okay, so I could put this all together if I wanted to. Let's see, I'd say that I have what? 1 plus J1 I1 minus J1 I2 is equal to 10. And then over here I've got what? I1 minus J1 I1 plus 4 plus J2 I2 is equal to 0. So you put this into a matrix. What's that matrix going to look like? So this would be 1 plus J1. This would be minus J. Then I would have minus J and 4 plus J2. I1, I2, this would be 10, and this would be 0. So if you put this into your calculator, it may not like this. I know with my HP I can do it this way, but some of the TIs are pretty finicky. If you have anything that's complex, you have to have everything that's complex, so it may insist that that's 10 at 0. That's fine. I guess this would be 0 at 0, right? You can play that game. So when you do that, you come up with I1 and I2. If you want to reproduce this at home or something, I'll give you I1 is 6.67 at an angle of minus 36.9, and that's just amps. And then what I really want is I2, which is going to be 1.49 at an angle of 26.6 amps. Why am I so interested in I2? Yeah, because what I'm looking for is V naught, so I can say that V naught is equal to I2 times 2 ohms, right? So I have 1.49 at an angle of 26.6 times 2, which gets me 2.98 at an angle of 26.6 volts. Questions of that? I mean, by far the most difficult part of this problem is probably right here, dealing with this. And you get better with that by practice.
Is this, are units RMS value?
Yeah, that's a good point. We're back to, remember, only 3 phases where we assumed RMS unless told otherwise. So with this, I would take this as not RMS, yeah. Other questions? Okay, well, like I said, lots of practice here, so we'll do lots of practice. How about this one? We've taken the 2 terminals of this, hooked them together, and put a resistor in there. That's fairly common. So let's take this current here. I'll just go ahead and assume this as I1. I could assume this is I0, but why don't I say that this is I2? And we'll know, of course, if we get I0, if we can find I2, we know I2 is equal to I0. So if I do then the loop for I1, what's that going to look like? Well, if I start here, I gain 24, so I'm going to say that that's a minus 24 at 0. And then what am I going to have? Plus, you ready to take a big jump here? We could do 4 and then minus J4 and plus J2, so that would be what? 4 minus J2 times I1. You okay with that? That gets me to here. Then I've got what? Plus 2 times I1 minus I2, because your net current going down is going to be I1 minus I2. And that gets me back to the starting point. I mean, if I didn't have to worry about the other part of the circuit, I'd set that equal to 0 and I'd be good to go. I'd have too many unknowns, but it would be easier to that point. But I know because I have some current over here, I2, I have one more term. I have this mutual term here from this thing. So what's that going to be? Well, it's going to be J1 times I2, isn't it? And we'll set that equal to 0. And now the work comes, is it positive or is it negative? Well, this I2 comes around here and enters this non-dotted terminal. So which terminal is going to be positive over here? Positive and negative, isn't it? So as I went around that in a clockwise fashion, I went from negative to positive. So this term would have been a gain. How do we treat gains? Negative. Okay. Everyone's good on that? Okay, let's do number 2. And again, I always just build up some momentum here. I'm going to do all of the self terms here. So I've got J3 minus J2, so I could say that this was 3 minus J times I2. There's J3 minus J2, so I got just 1 J. We got 3, so 3 minus J. And then I'm going to have plus 2 times now I2 minus I1, because I'm looking at the net current going up through that one. That gets me back to my starting point, right? but I have to take into account this current I1. It came around here and it went into the dot. So going into the dot, it's going to induce voltage positive at which terminal over here? It goes into the dot. I1 goes into the dot, positive at the dot. So we'll go from negative to positive. As we go from negative to positive is a gain. How do we treat gains? Negative. Okay, so I have something like that. We could tidy this thing up. What do I have for I1? I have I1, I2. How many I1s do I have? 4 is 6. 6 minus J2. How about I2s? Minus 2 of them. Oh, and I got another J. So minus 2 minus J. And that would be equal to 24. Then over here, what do I have for I1s? I've got minus 2 and a minus J.
I have a question.
Mm-hmm.
How do we use the first one, we're using the current, the second current on that the last term.
Right here?
Yeah.
Okay.
We're using the second and 2 on when we're analyzing loop 1.
And then when we're down here, we use I1, don't we? Okay. Yeah, it's because this current here, I2, is inducing a voltage over here. And conversely, this current I1 is inducing a voltage over here. So I mean, that's what I said when we first started studying transformers. Everyone is pretty comfortable with taking this transformer and having this current, I1, induce a voltage over here. So have this voltage here as some function of I1. Everyone's pretty comfortable with that. But truth be known, the voltage across here, I mean, if you put some resistance in here, so now you have some current I2, the voltage across here, the other side of the story, this voltage across here is a function of I2. It goes both ways. Okay, with a linear transformer, it goes both ways. Okay. So that's always kind of a litmus test. If I write an equation and I only have one current in it, I know something's wrong if I got a mutual problem. Yeah. Good observation. I think so, yeah. Yeah. I could have probably just substituted that, but I kind of get in the habit of I1 and I2. Let's see, if I got all the I1s grouped up, how about I2s? I got 2 resistive and 3, so it's 5 minus J is equal to 0. So you hammer that into your calculator. I'll give you I1. You really don't need it, but if you're checking this out at home, 4.07 at an angle of 26.7 amps. And then I2, which is what you want because you know that's equal to I naught. We could do that by inspection. I naught is 1.78 at 42.0 amps. So that would be our answer. Questions with that? Yes?
Based on that, not all of us have really extended frequencies of
Okay.
Are we going to face a system with more than 2?
Oh, you'd probably just have 2. Yeah. Or you could try a problem like this next one, where no one's calculator will help them. This is a little bit like during the Inquisition, right? Before they started to torture you, they would show you the tools, and the weak people would probably recant before even the things got real rough. Okay, so we look at this problem. We know this is not going to be pretty, right? I mean, how many terms? If I look at this as I1, if I look at loop number 1, how many terms? Let me put the terms in terms of self and then mutual. Okay? So as I go around here, we're going to have a term for the voltage here, so that'd be 1. And then for the resistance, another one. Self-inductance, another one. Self-inductance here, another one. Capacitance. So it looks like I got 5 self terms there, right? Now how about mutual? Well, let's see. Does the current in this one induce a voltage here? Indeed it does. Does the current in this one induce a voltage there? Yes, it does. Does the current in this one here induce a voltage here? It sure does. Does the current here induce a voltage there? Yeah. So we should have 4 mutual terms and 5 self terms. Okay. How about loop number 2? Good thing the multiple choice test is looking up all the time, isn't it? Yeah, write-out test. This would be a nightmare to not only take but to grade, because you can start to influence the signs on these things by whether you assume the current going to the right or to the left. You might have a negative sign. I might have a positive sign. We might both be right because we've assumed different currents, right? Yes, this can get fairly ugly. Okay, loop number 2. That's this one up here. So I've got a self term there, a self term there, and a self term there, right? So self is 3, mutual. How many mutual terms are we going to have? Well, we've got the current in here inducing a voltage there. We have the current in here inducing a voltage there. We have the current here inducing a voltage there. And we have the current here inducing a voltage there. So we still have 4 mutuals. Okay. And we could go through that for loop 3. So when we when we get together next time, I'll pull this thing out and we'll see if we can go through this. So you may want to go in. I'll make sure this is on the 5th page of the PDF. Print this out and we'll go through it. Better yet, print it out and try your hand at it before we meet next time. And we'll go from there.